Yeah, so that's where we left last time. We had the introduction, we had the definition of RUG, and we did the text embedding and vector search. And now we're gonna look at some tools and frameworks, so for information retrieval. So let's check that out. So a library that is often used for similarity search, I've just mentioned, is called FAIS, which stands for Facebook AI Similarity Search. And it has been developed by Facebook AI and optimized for vector embeddings. Its key features are that it can handle very, very large data sets efficiently because it also supports GPU acceleration and has flexible indexing options like fed or inverted file. And because it supports saving and loading indexes, it is often used as a vector search for recommendation systems or for retrieving similar documents or similar images. So let's try to build something similar as before or as last time, but this time we load some long articles as our knowledge base. For example, we can use the Wikipedia API to do that again, and then we convert them into embeddings. But this time we store them into our database, into our FAIS index that we can now query against. Okay? So it's a two-step process. We start with the first one. The first step is to create and cipher the FAIS index, and then the second step, which you try to do on your own, will be load and update the FAIS index with new article. So first of all, you probably need to install this here. I think we have to install this and this, but probably you need to install this as well to just run it, just to make sure. And then we need some libraries. What we want to do is we need to load some information that we can data use as our knowledge base for queries. And we just use Wikipedia and load articles using, again, the Wikipedia API. So that's the first thing we need to import. We're going to import the Wikipedia API. Also, we need, again, the sentence transformers. And we're also going to need the util package again. Also, we need FAIS because we want to store our embeddings. And we need a pickle file where we save our articles, because these two are separate from each other. I think that's it for importing libraries. So again, this is probably the same code as we used last time. So to use the Wikipedia API, we have to create a custom agent. We can also just copy paste the edition launcher. And then we're gonna load some pages, so just some Wikipedia articles, and we put them in a list. And I'm gonna use the same as we used last time, I think, which was the Summer Olympics. Oops. With a Wilcott. The Weight Euro 2024 and the US Open. Okay, put them in a list, and then we create a new empty list with our embeddings. So now we can create a wiki object. We query the API. We use the English side again. For headers, we use our custom agent. Then we're gonna loop over all the pages of our list. If the page or the article exists, we're gonna append it to our list. Or we append the text of the article to our list. And then we're gonna also save the articles in this pickle file. I'm gonna save it in my folder data, and I call it wiki pages.pickle. Then let's print out a success message as well. Let's also say how many articles we were able to retrieve. Okay. What's the problem? You have a underscore user agent headers user underscore oh yeah, thanks. Thank you very much. All right, depending on the API, this takes some time. We retrieved all 3 articles, which was expected, as I think we have already done this before. So now we create a text embeddings with those Wikipedia articles. We've also done this last time. So we do exactly the same steps. We load a pre-trained transformer model, and then we encode the articles into embeddings. Then we add our calculated embeddings to our newly created FICE index, so that later they can be searched for queries for nearest neighbors. Before, we have to get the number of features in each vector, and then we create a flat index, which is a non-hierarchical list of vectors for storing and searching vectors based on the Euclid distance again, which, if you remember, is a straight line distance between 2 points. And then we're going to save the FICE index to a file on a disk. So this way we avoid recomputing the index. Embeddings for all articles, and we can also share the index with others if we want to. So let's start with computing the embeddings. We use the sentence transformers. We use the same model I think we used last time, which was the all mini L6 V2. And then we can create the embeddings. Initialize the embeddings using model and code. And we hand over our articles. We don't want to convert them. So let's put that to false. And then we create the index. For this, we need to get the dimensions first. And then we can create the index. Using this Euclid distance and calculated dimensions. And then we add these embeddings to our database, so to speak, to our files indexed. So we do that by calling add and handing over the embeddings. And that's it. Now we can save it to our disk by just using write index, using the index, and then specify a hash. I'm gonna call it Mickey embedding, not index. And then let's also print out a success message again, where we also put in how many indexes have been created by using length again. Let's also print out how many articles we had. Okay. So let's try that. Sentence, transformers, too much S. Okay, yeah, this can take a little bit. So we should expect, because we have three articles, we should expect that 3 embeddings for these 3 articles will be created. And then we can take a look if the files index file has been created in our data folder. Next step would be, again, create embeddings, but this time for an example query. So we used, again, the same model, of course, to create the embeddings, which is mandatory. And then we calculate which is the most relevant article to answer our example query. We can start writing the code for that until the creation of the embeddings is finished. So we will have a query. We're gonna use again model encode, and let's just come up with a relevant question. Let's say, who is the best marker in currently? So yeah, we have articles for Summer Olympics, for UEFA Euro and tennis. So let's come up with a question regarding soccer, and then we should retrieve this article as the best to answer the question. Okay, Albert. So now we have the embeddings, we have the query with the embeddings. Now we have to search our files index. And to do that, we use the distances. And here, with this parameter, you can specify how many results you want to get. So for example, it could be that you want to get the 3 best articles. In our case, it doesn't make any sense because we just have 3 articles. But let's say you want to build a RAG system for your internal web page or for your internal Wikipedia page, and you want to get the best matching 3 articles. So with this parameter k, you can specify how many results do you want to get. We want to get only the best results, so we put k equals 1 there. That's the top, meaning only the top match. Let's print out something so we know what's happening here. So we're gonna say that's the nearest neighbor. And then let's print out which is the nearest neighbor. And we again use the index to retrieve the name of the best matching article. So let's see. Okay, just for checks. Okay, seems to work. So let's save it. So it's basically the same that we did last time, but this time we also now saved all of our embeddings, so we don't have to create it anymore, and we saved it here in this wiki embeddings index file. Then our next step, save it again, would be to update and first load our index file and then update it. Like, for example, if you use it for any company website or something like that, and you have new articles or want to create new embeddings, you first want to load those that you have already been created, and then you want to update it, and then not just check if you can use it again as we did. And again, we're going to import our relevant libraries. You can just copy paste it if you like. Exactly, we need exactly the same libraries, Wikipedia, API, because we want to load some additional articles, sentence transformers. Suffice, and also pickle. Right. So now we can update our knowledge base with new articles from Wikipedia by calculating their embeddings again, and then we're going to add them to our files. We don't have the embeddings right now, so we need to load them using the read index method. So again, we put this into a variable called index, and we use the read index method to do that, and then we hand over where our index file is located, and mine is called wiki embeddings. And let's also print out how many articles are in that. I mean, we know it, but just to make sure, it's good to add checks. Number of items in the loaded index. We can use the number total method to print that out. Oh, right. Should be 3, right? Earnings. Wiki bad things. Okay. Good. Let's save it. So now we're gonna load and update our articles. So if existing, we're gonna load the articles. If not, we're gonna create new articles, load the article and save them again. So this define our custom user agent again. Again, you can just copy paste it if you like. I'm gonna save my new articles in a new list called new pages. And what are we gonna do? Let's do the latest Super Bowl. Just should be an article about that. And we're gonna save the article again in a list called text. All right. Same procedure. So again, let's check if the article exists. Let's add a try and error this time, just for practice. It's good practice. So let's check if there is an existing articles page. Where we're gonna save our articles. We're gonna save two things. We're gonna save the pages, which we will find in data pages, and we're gonna save the text, which we're gonna find in data text. And let's print out how many articles we have in our file currently. Then we're gonna check how many pages are in our picker file. And then and accept if there is no, if we don't find anything, just do an accept file not found ever. This is optional, it's just we practice. So if we haven't found anything, if there hadn't been any picker file created, we just gonna initialize them empty. And also print something out for the user that there has been no existing pages found starting fresh, for example. So now we're gonna loop over the found pages if you have found something and add them to our list. So let's do for page name in new pages this time. And if page name, you're gonna check if this article has already been added or if it's already in our database, so that we don't have duplicates. As we don't want that. Like imagine if you build a database with embeddings for by scraping a website, let's say a blog, and you let this script run every day, you could, yeah, you don't have to check for dates or anything. You can just run it, and the by adding this, if page name not in pages, you just make sure you don't get articles. You don't create embeddings for articles that have already been created. Okay. All right. So if it's not already there, we're gonna do page name. And then if the page exists on Wikipedia, we then append it. We're gonna append the page name as well as the page text. And then we're gonna save it again to our updated version. And select the pages as well as the text, like we did in the last notebook. And then let's print out how many articles we have now in our file. Okay, let's try it. Great, as we can see, as it reaches this point here, after loading our database, we have 3 articles in it. And now we are looking for this new article, the Super Bowl article, and it has been added. And after it has been added, this statement here prints out. We have now 4 articles in our updated file, which is great. So that's how you update it with new stuff, and also checking for duplicates. And now we only have to create embeddings for this new article of Super Bowl. So, and then we create embeddings for our query. Okay, so now that we have covered that part, we now know we build embeddings and we know how to save them, and we know to do a vector search and to select the relevant data. And we now want to learn how to feed the data into the LLM model, which is this box here, to answer our questions with this information. And then we have built a complete RAG system. What do we need? Basically, we need what we have already imported, but also we use OpenAI, but of course we need sentence transformers again. We need files, because once again, now we load our database with 4 embeddings and also our pickup file with 4 articles. We use OpenAI as our chatbot, or we use one OpenAI model as our chatbot, and I think that's it. All right, so let's load our index again using the read index method. Embeddings. The embeddings is our file name. Again, let's make a quick check just to see how many articles we have loaded. I just like to do that just to make sure, and also to separate the code a little bit. Yeah, and then we try to load the existing articles. Yeah, that's the same as we have already done this in the last notebook. So we just load all articles, and we load all pages, and we load all the text of the articles. So we save the pages in pages, and it will find this in data pages, and we save the text in text, which is under data text. Okay. Again, a success message. We can continue in the meantime, again, with computing the embeddings for a query. Use the same model again. Again, let's use a question which we should be able to answer with one of our articles. And again, this is a question more like GPT-4o shouldn't be able to answer out of the box because it's too new. But all the information is just in the article. We have just loaded from Wikipedia. Okay. And then we create the embedding for this question. Let's quickly run that again. Okay, now I'll ask the embeddings as well. And then we're going to search our index. So again, we use to calculate the distances. We only want to get the top article. And I'll loop over all the indexes. And save the best article and matching article. Because this is what we want to hand over to our LLM model. We're going to save the full content and matching article. Let's print it out as well, just to make sure we have found the best one. quickly check it. After that, we should be all set if this works to now create or call our large language model with. We have to write a good system message and then also a prompt which uses this article as a context. Yeah, let's first set the API key. Again, don't do that, okay? We just do that here in our lecture. But don't hard code your API key here. Everybody has an API like this. It's just for this lecture, okay? So we're gonna initialize our client, which is an OpenAI client, and we use our API key for that. And then, well, we're gonna use, which model we're gonna use? Let's use GPT-4o. And we need a system message and a prompt. So for the system message, you are an intelligent assistant designed to answer questions accurately and concisely by, this is important, by using provided content. Let's make it really clear and say, just to emphasize, sometimes you have to be really specific that you don't want the general knowledge of the LLM to use to answer the questions, but the content or the context. Your goal is to prioritize information from the documents and resources available, ensuring that responses are grounded in the retrieved content. Let's also define some key guidelines. We're gonna go deeper into this topic of writing with prompts or even prompt engineering and system messages in a label lecture. But let's just use some key guidelines, which is also always a good idea. Use only provided content to answer questions. Do not make assumptions. Or include information that is not explicitly mentioned. Let's do one more. Let's say when appropriate, provide a context or clarification beyond retrieved document. Okay, let's leave it at that. And then Let's do the prompt. So the following content is provided to help answer user questions. Content. And we had saved the content in matching content. So that goes here. Then comes the user question, which we have saved in user question. Then let's tell the model once again, please use this content to answer the user's question as accurately and concisely as possible. Okay. I think that's fine. Matching content. The article. Okay. And now we're gonna send our request to our API and catch the response. That's the basic syntax of calling OpenAI API. We can hand over the model we have specified, and then also the messages, which are we need two things. We need the system message and the user message. So this first one, the first row is system, and the content of system is in our system message. And then the second one is row user, and the content is our prompt. And then we fetch the response. Which we find here under message content. And that's a basic OpenAI syntax. You can copy paste it also from the documentation of their website. And then let's print it out. Let's print out the question again. And it worked. So you see, to answer this question, it used this Wikipedia article, and that is what a RAG system is all about.